Alright, let's go ahead and take a look at Chapter 10 material and work through some examples here together. I'll just go ahead and get started with example 10.1. Calculate the overall change in internal energy delta U, this needs to be in joules, for a system that absorbs 188 joules of heat and does 141 joules of work on its surroundings. We'll just go through the strategy and solution here. This is fairly straightforward. Our strategy is combine the two contributions to internal energy. Using our formula delta U, which is internal energy, is going to equal Q plus W, where Q is heat and W is work. Now it's important to know that if the system absorbs heat, our Q is positive, and if the system releases heat, then our Q is negative. And Q and W will, you want to make sure that you pay attention to the sign. So, for example, we know that the system absorbs heat, because it tells us, system that absorbs 188 joules of heat, and then does 141 joules of work on its surroundings. So if it absorbs, it's going to be positive. If it does something to the surroundings, it'll be negative. So what that means is that our 188 is positive and our 141 is negative. And if we look at our difference here, 188 minus 141, our overall net is 47 joules. So this would be our overall energy change. So this would be an absorbing of energy. You can look at table 10.1 in the text to make sure that you've used the proper sign conventions for both heat and work. Alright, so let's go right on to the next one. Example 10.2. Determine the work performed or done in joules when a sample of gas extends from 552 milliliters to 891 milliliters at constant temperature. And we have a few parts to this. Part A, and this would be against a constant pressure of 1.25 atmospheres. Part B, against a constant pressure of 1 atmosphere. And part C, against a vacuum. And then one thing that we're given as equality is 1 liter atmosphere is the same thing as 101.3 joules. So if you're still following along here and haven't paused it yet, our strategy is to first determine the change in volume. Change in anything is represented in multiple classes. For example, chemistry and physics is using this uppercase delta, which just looks like a triangle, which represents change in. So determine the change in volume. We need to identify the external pressure, which is given the variable capital P. And we're going to use our formula for work. Work looks at change in, we'll look at a external pressure versus change in volume. Work can be calculated by looking at the product of pressure and change in volume. Our result is going to be in liter atmospheres, and that will allow us to get back and forth for volume, pressure, and energy. So 1 liter atmosphere is 101.3 joules. So if we look at these three parts, starting with our change in volume, this is down at the solution at the bottom, we're looking at our gas expansion. So we're going final minus initial, which is 891 minus 552. That comes out to 339. For part A, our pressure, it says against a constant pressure of 1.25 atmospheres. So if you follow along, and let me move my cursor, we're going to look at our pressure times delta V. And the formula for work is negative PV. So a negative 1.25 multiplied by the volume difference, which we already calculated, is 339. This is atmospheres milliliters. So what I would do is, if you want, go ahead and do an equal sign. Multiply these two out, and then see your units are atmospheres milliliters. But we need to get our answer in joules. And we need liter, let's see how they work this out. We need liter atmosphere so that this will work out for joules. And there's 1,000 milliliters in a liter, so that converts this milliliters right here. And then we can also cancel out liters, where I'm highlighting here and here, using the conversion of milliliters to liters. And then we're left with joule atmospheres. 1 liter atmospheres is the same thing as 101.3 joules. That will take care of the atmospheres here and here. And you can see units cancel again. Atmospheres, I just highlighted the milliliters and the liters. And then that leaves us with an overall negative 42.9 joules. We could do the same thing against a constant pressure of 1 atmosphere and see what that looks like. Everything is the same except substituting in negative 1.00 instead of negative 1.25. Again, convince yourself how the units cancel. You get negative 34.3 joules. So this is useful information in this problem. You can see what it's like at a constant pressure of 1.25 against a constant pressure of 1 atmosphere. 1 atmosphere is about sea level. This would be a little bit below sea level. And then in part C, it says to look at it against a vacuum. A vacuum is where you have 0 pressure. So in a vacuum, if it's 0, everything cancels out and you get 0 joules. So that's just to illustrate that it will be 0 in a vacuum. Remember that the negative sign in the answers to part A and B, what that means is, think about positive and negative as you go back to and think about 10.1 and look at that table. It will indicate that the system does work on the surroundings. If it's positive, it's on the system. For example, when an expansion happens against a vacuum, no work is done, so then that represents our 0. And again, just reading along with me, this example illustrates that work is not a state function. For an equivalent change in volume, the work varies depending on external pressure against which the expansion must occur. So depending on the pressure of the system in the surroundings, there will be a different amount of work. All right, move on to example 10.3 with me. It says, given the thermochemical equation for photosynthesis, and this is already balanced for us, and it also gives us a delta H, which is an enthalpy value. And it gives us the sign of this as positive. It says, calculate the solar energy required to produce 75 grams of glucose. And our formula here is written 6 parts water, liquid water, plus 6 parts gas state carbon dioxide produces 1 part solid glucose and 6 parts molecular gas state oxygen. Our strategy here is to take the thermochemical equation, and what it shows is that for every 1 mole of glucose produced, we're going to get 2,803 kilojoules absorbed. Again, the positive sign lets us know that it is absorbed. And what we do is we need to then find out how much energy is absorbed for the production of 75 grams of glucose. So this is getting into a little bit of stoichiometry, which we're pretty familiar with, and hopefully you've had a lot of time to practice with it, so this shouldn't be too difficult. We must first find out how many moles there are in 75 grams of glucose. And if you remember, and I'm sure you do, to go from mass to moles, you need to use molecular weight. So if you add up 6 carbons, 12 hydrogens, and 6 oxygens, you should get something along the lines of 180.2 grams per 1 mole. If we take 75 grams of that glucose and we multiply it by the ratio of the molecular weight, and we want to arrange it so that the mass and grams cancel, we'll be able to calculate our moles. So then 75 divided by 180.2, and if they wrote the math correctly here, should be 0.416 moles of glucose. Then we can multiply the thermochemical equation, including the enthalpy change, by this molar amount. And this comes from the mass. And then that will allow us to write the equation in terms of the appropriate amount of glucose. So let's continue on. So we're going to take our moles that was just calculated, the 0.416, and we will use our equation here and then our enthalpy value. So essentially you're just taking your enthalpy, which is 2,803, and then multiply it by 0.416, and you get this value, which is 1.416 0.17 times 10 to the third kilojoules. The sign doesn't change, it still remains positive. We can also multiply the 0.416 times the coefficients, which is shown in this top part in brackets. Just take your balanced equation, and then you have these ratios here, and this is just showing you that with 75 grams, it is less than what is stated in the original equation. So it'll be 2.5 parts water, 2.5 parts carbon dioxide, 0.416 parts of glucose, and 2.5 parts of molecular oxygen. What this means is that this value, the 1.17 times 10 to the 3 kilojoules of energy in the form of sunlight, is consumed in the production of 75 grams of glucose. Note that the per mole units in enthalpy are canceled when we multiply the thermochemical equation by the number of moles of glucose. One thing to think about is the specified amount of glucose is less than half a mole. This gets into this equation here. Normally we won't write it like this. You usually want whole numbers when you're working with equations, but this is just showing you with stoichiometry what parts you have of each component if you use less than 1 mole of this. Of course, if we use 1 mole of glucose or produce 1 mole of glucose, then these are their normal values of 6 moles of water, 6 moles of carbon dioxide, and 6 moles of oxygen. If we produce 2 moles of glucose, then you would just double everything. But since this is a fraction, then these will be fractions as well. And that's all that's showing. It's just showing what the molar amounts of each would be. So to continue, it says the specified amount of glucose is less than half a mole. I'm just repeating that. Therefore, we should expect the associated enthalpy change to be less than half the specified in the thermochemical equation for the production of 1 mole of glucose. So again, this value is also less, and it's a fraction of the original. And then if, as I was mentioning, if this was 2, then this would just be doubled. Well, let's take a look at our fourth example. And this reads, calculate the amount of heat in kilojoules required to heat 255 grams of water. And it gives us the temperature range that we'll go from. And this looks like about room temperature, 25.2 degrees Celsius, to just under the boiling point, 90.5 degrees Celsius. We're going to use what's called the heat equation, which is ms delta T, or it's written here Sm delta T. And we have a few constants. One of them is specific heat, which is this S. And this is for the specific heat of water. And this is a constant. This doesn't change. This is 4.184 joules. And the units are joules per gram degree Celsius. So joules in the numerator, grams times degrees Celsius in the denominator. Our mass here is 255 grams, which is the given. This formula, you want to pay attention to the units so that we can get out joules, grams, or degrees Celsius. So if this given mass was in a different unit like micrograms or milligrams or kilograms even, then we want to convert it back to grams so that it cancels with the grams in the specific heat constant. And if the temperature was given in Fahrenheit, we need it in Celsius so that it cancels again with these degrees Celsius. So the formula is specific heat mass and change in temperature. We want to find what our change in temperature is. And when you find the change in, usually it's final minus initial. The final temperature is 90.5. The initial is 25.2. We find the difference there to be 65.3. So now we can plug all of this into our formula for heat. We're going to use our specific heat constant for water, our mass of water, and then our delta T. Notice that the grams cancels and the degrees Celsius cancels. This leaves us with an energy unit of joules. 4.184 times 255 times 65.3, we get 6.97 times 10 to the 4 joules. If it's a big number like this, something like 10 to the 4th, we can divide this by 1,000 and get a friendlier number like 69.7 kilojoules. A lot of these values will be in kilojoules because they're just 2 digits, like in the tens or in the hundreds. Look carefully at the cancellation of units, as I mentioned, and make sure that the number of kilojoules is smaller than the number of joules. It's a very common error to multiply by 1,000 instead of dividing in conversions of this kind. Continuing on into example 10.5. And again, you, of course, pause the video as you need to, and I'm sure you've been doing that, but just to remind you, pause things and write down what you need to. Let's go ahead and read this one. A metal pellet with a mass of 100 grams, originally at 88.4 degrees Celsius, is dropped into 125 grams of water that's originally at 25.1. The final temperature of both pellet and the water is 31.3 degrees Celsius. We need to calculate the heat capacity of the pellet. So we have a couple things here and that are important to mention really fast. The specific heat of water is a constant, and we do use that, which is the S from the last formula. The heat equation is going to be used again, but this time it will be used with C delta T. C is usually used as specific heat of some type of material that you're calculating. S is used for water. So to continue on just reading the strategy, follow along. It reads, water constitutes the surroundings. The pellet is the system. We can compare that by using our heat of surroundings, which will be ms delta T, which is the same formula as the last example. That will allow us to determine the heat absorbed by the water. We can then use the formula Q equals C delta T to determine the heat capacity of our metal pellet. So let's take a look at this, and I'll mention another important thing. We're going to start with the determination for water, and this is just a repeat of the last example with different numbers. Our mass is 125 grams, and I'm just reading right here. The specific heat of water is a constant. It's 4.184 joules per gram degree Celsius. And then our change in temperature, notice that the final temperature is 31.3, the initial is 25.1. We find the difference there is 6.2. Alright, so then what we get when we calculate our Q, and our Q again is ms delta T, it gives us not only the heat of the water, but it gives us the heat of the pellet. Because when you put the hot pellet into the room temperature water, it does heat up the water, but they're going to reach a steady state where the water temperature increases and the metal pellet temperature decreases, both of which will be the same temperature. So you'll let it stabilize. If you had a thermometer in here, you could watch the decline of the temperature or increase of the temperature, and then it will start to plateau and have like a flat line. And then you can figure out like a range of that flat line that looks really nice and flat, and then you can use that as your average temperature of both together. At that steady state, where they're both the same temperature, they'll be equal and opposite. So the heat of the water is going to be the negative heat of the pellet. So the hot pellet is losing the temperature, it's going down, and the water is increasing temperature. Some other things before we move on to the solution is the mass of the pellet is 100 grams, and our change in temperature of the pellet is going from 88.4 to 31.3. Again, do final minus initial. A lot of times you'll want to do the large number minus the smaller, but remember it's final minus initial, and it does come out as a negative value, and that's okay. And it should. If you want to pause the video now, try the solution on your own and see if you can, and then come back and check it. It's not a bad idea. Alright, so let's now take a look at this solution, and sorry about the slide flip-flopping. I needed to actually put this information in. So following along with me, we have our specific heat of water, which is a constant, 4.184 joules per gram degree Celsius, our mass, 125, and our delta T, 6.2. This gives us a heat value of 3,242.6 joules. And then again, the heat of the pellet is equal and opposite, so it's opposite in sign, so this is just negative 3,242.6 joules. We can use our formula Q equals C delta T. We'll have our heat, which we can get from the opposite sign of the heat of water, and then we have our delta T, and then that will allow us to solve for just the C. Plugging it in just as the formula is written, we have our heat, which is negative 3,242.6. That's going to equal our specific heat of the pellet, multiplied by the change in temperature, negative 57.1 degrees Celsius. If we take the joule and divide by the degrees Celsius, we'll get our specific heat. This would be 57 joules per degree Celsius. Notice the negative divided by negative cancels out, so it gives a positive value. So you will not have a negative specific heat. So we get 57 joules per degree Celsius for our specific heat here. Again, the units do cancel properly. It gives the appropriate units for heat capacity. Moreover, the change in temperature of the pellet is a negative number because the temperature of the pellet decreases, and we mentioned that before. I'm going to record this video into two different parts. This will be the end of part 1. Look for part 2 to be posted later. Thank you.